Monoclonal antibodies. A deep dive into classification and mechanisms. Welcome, listeners, to today's episode where we explore the fascinating world of monoclonal antibodies, a revolution in targeted therapies, and truly one of the cornerstones of modern medicine. Let us begin by understanding what monoclonal antibodies are. These are proteins engineered in laboratories to mirror the remarkable abilities of our immune system, specifically designed to recognize and bind to one site on a target molecule. This extraordinary specificity enables monoclonal antibodies to target disease with remarkable accuracy, minimizing unintended effects. Now, let us turn to the classification of monoclonal antibodies, which derives both from their cellular origins and their molecular composition. At one end of the spectrum, we have murine monoclonal antibodies, built entirely from mouse cells. While these were pioneering in early development and relatively inexpensive, they provoked strong immune responses in patients, limiting their utility. Advancements led to chimeric monoclonal antibodies, where the binding portion originates from mouse cells, yet the rest of the molecule is human. These hybrids offered reduced risk of immune reaction but did not eliminate it. Further refinement brought us humanized monoclonal antibodies. Now, only the regions that interact directly with targets are derived from mouse cells, with the majority of the molecule being human. This evolution significantly improved patient tolerance and safety. Today, fully human monoclonal antibodies represent the gold standard, created using advanced biotechnology such as phage display or specialized transgenic mice. These proteins are nearly indistinguishable from our own antibodies, thus minimizing the chance of unwanted immune responses. There are also conjugate monoclonal antibodies, a versatile branch where the antibody is coupled with another active molecule. One prominent example is the antibody-drug conjugate, in which a cytotoxic drug is attached to the antibody, allowing precise delivery to diseased cells. Alternatively, radioimmunoconjugates pair the antibody with a radioactive compound, permitting targeted imaging or therapy. Next, let us discuss how monoclonal antibodies work. Their therapeutic effect depends on both their structure and the targets they are engineered to engage. There are several principal mechanisms. First, we have direct action, where the antibody interferes with its target. Neutralization is a common approach, in which the antibody binds to a soluble molecule such as a cytokine or toxin, physically blocking its interaction with receptors and thereby preventing harmful effects. For instance, one monoclonal antibody binds with tumor necrosis factor alpha, a key inflammatory molecule, helping manage autoimmune diseases like rheumatoid arthritis. Another direct mechanism is receptor blockade. Here, the antibody attaches to a cell surface receptor, obstructing its normal ligand from activating it. This action can be life-saving, as seen in breast cancer therapy, where a monoclonal antibody binds to the HER2 receptor and inhibits signals that drive unchecked cell growth. Occasionally, antibodies act as agonists, that is, they activate a receptor rather than block it. This rarer mode of action can be harnessed to trigger beneficial signaling pathways, as seen in certain cancer therapies. The second major category encompasses immune-mediated mechanisms. In this scenario, the antibody recruits the patient's own immune system to destroy the targeted cell. For example, antibody-dependent cell-mediated cytotoxicity occurs when immune cells such as natural killer cells recognize antibodies attached to diseased cells and respond by eliminating those cells. Another powerful method is complement-dependent cytotoxicity, wherein the antibody activates a cascade of plasma proteins that ultimately puncture and destroy the target cell's membrane. One of the most groundbreaking innovations has been checkpoint inhibition. Some monoclonal antibodies target regulatory receptors on immune cells, releasing natural brakes that cancer uses to avoid immune attack. By blocking these receptors, the immune system is unleashed to seek and destroy tumor cells. Finally, there are antibodies designed for targeted delivery. In this approach, the antibody is paired with a potent drug or other agent. When it binds to its specific target, often a tumor cell, the entire complex is absorbed into the cell, where the payload is released, resulting in precise treatment with minimal harm to healthy tissue. In summary, monoclonal antibodies are a testament to the power of modern science and biotechnology. Their journey from murine origins to fully human molecules represents a triumph in drug design. Their diverse mechanisms, ranging from direct blocking and neutralization, to enlisting the immune system, to delivering targeted therapies, have transformed how we fight cancer, autoimmune diseases, and other life-threatening conditions. Thank you for joining us on this exploration of monoclonal antibodies. Stay tuned for more insights as we continue to unravel the wonders of contemporary medicine. It's the Everything Surgery Podcast. Dissect the extraordinary.